All right, so we are here tonight to talk about graphing as a gateway to analysis, as well as to introduce DataClassroom U. This is a series of new features that we've been working on over the past year. Chief among them, the ability for your students to get started with working with R code. So we'll highlight that during this presentation. It also has some more advanced statistical features that we won't necessarily cover in this presentation, but that is a part of DCU as well if your students want to do more advanced analysis. So tonight, I'm talking about graphing as a gateway to analysis. We bring this up in a lot of our webinars. The key here is that by visualizing data, students are better able to discern patterns in the data and progress through their analysis. So really, we do not want graphing to be the end of a student's investigation, and we're going to do that tonight. So we're going to do that specifically by showing a progression of graphs and kind of a natural flow of questions students might ask when looking at different graph types. We're also going to focus on encouraging students to determine the real meaning of a p-value. Too often, students limit their understanding of a p-value in statistics to what is statistically significant and making it into a binary distinction between significant or not significant. But really, there's a lot more room for interpreting data as meaningful beyond that. Like I mentioned, we're going to talk about how we can help students develop familiarity with common commands in R. And what we've done is taken the graphical user interface of DataClassroom and how easy it is to make different graphs and perform statistical analyses, and then see the R code that's necessary to generate what you've done in DataClassroom. We think that's a better entry point for students than handing them a manual of all the commands and syntax that they're not familiar with and expecting them to learn R that way. And if we have time, we're going to talk about how it's important to allow students to make observations that aren't necessarily restricted to the outcomes of inferential statistics. So there are a lot of things that you can see about data. You can tell about the story that data is telling you without relying on a t-test. And we're going to do all of that tonight with a data set I worked on over the past couple of days, focusing on the World Cup. So I hope we were presenting a topic that's relevant and interesting to students. So the story goes back a couple of years. I was talking with some friends about the World Cup, picking what teams to cheer for. And it is basically a pub level fact. Like I picture the three fans who are always in the pub in Ted Lasso, the kind of thing that they would take as canon, that South American teams struggle to score when they play in Europe. And I thought, okay, let me investigate this fact and see if there's this myth and see if there's any data to back it up. I focused on Uruguay, Brazil, and Argentina because they are the three most successful teams in South America. They're all top 10 in all-time appearances in the World Cup. They also have a disproportionate share of success in the World Cup. They've won 9 of 21 FIFA World Cups. That's over 40% for these three teams. And that's higher than any three-team combination of teams in Europe. So I kind of love this South America-Europe rivalry. And then finally, kind of investigating what's underlying all of this is the idea of a home field advantage. Of the 5 World Cups played in South America, 4 of those times was won by a team in South America. So thinking about it, I really tried to focus on dialing in my research question. It's another thing we always try to emphasize is asking a very specific, clear research question that will guide how we collect our data. And my question was, is there a meaningful difference between the number of goals South American teams score in South America and away from South America? So to take us through the data set and other best practices in teaching data science, I'm going to turn it over to Aaron.
Okay, yeah, thanks for that setup. I also love this question because it's just really interesting, and I also loved your use of the phrase pub level fact. I think that's really good, and we can apply the scientific method to this kind of question, and see how pub level facts hold up to actual data. So with that, let me just give me 1 second to share my screen, and I want to share this screen. So I'm here in the dashboard of DataClassroom. If you are not familiar with DataClassroom, you'll know that you can upload your own data or you can work through stuff that's in our resource library. And this data set that I'm going to work with, you will not find in the resource library yet because we have yet to put out the final version of it. But if you do go to the Browse tab and you go to data sets and you search any data set. If you search the term World Cup in there, you will find this data set. So it won't be anywhere near the top, but if you search any data set, so over here on the owner filter, I went to any data set, and then I put World Cup up into my search bar up here in the upper right. So this is the data set World Cup goals scored by South American teams, and those three countries that we have data on here are Brazil, Argentina, and Uruguay. Those are each row in the data set represents a different World Cup performance from a different year from one of those three countries. And I'm gonna go over to the graph tab, and to navigate there, I just went over through the tab on the top of the screen where you see table, graph, and then there's this getting started. But I went over to the graph, and we'll start diving in and exploring this question. And so, sort of the larger question is here is, is there a difference in performance when these South American countries are playing in South America or when they're playing in Europe or elsewhere in the world? Our proxy for performance is going to be this number of goals scored. And part of the reason that this, I think, is and I'll show it so we can plot number of goals scored. Part of the reason this is probably the best measure of performance that we could use in this case is just kind of the format for World Cup. Doing win percentage is going to be sort of difficult in a tournament that's ultimately elimination, and then it becomes even more difficult when you factor in that you have the sort of round robin style play and the pool play before you get to the elimination rounds. So we're going to look at number of goals scored. I first visualize this as the dot plot. You could also take a look at this as a histogram or frequency plot. And I'm working in the control panel on the right. One thing you might want to do at this phase when you're sort of just like looking at your response variable is you might want to overlay a normal distribution on it. And I guess what I see here is that these data look a little bit non-normal, but they don't appear to me to be sort of violating this normality in any kind of like skewed or systematically skewed way. Like it doesn't look like it's all a heap with a long tail, or it doesn't look like it's like normal skewed to one side. We can run some tests for normality on this, and there's two different normality tests in here. When we run the D'Agostino-Pearson test, where the null hypothesis is that the data are normally distributed, we get a 0.157. So we'd sort of fail to reject that null hypothesis of normality. When we run an alternate test, Shapiro-Wilk test, we get a 0.03 where you would reject normality. But this is one of those cases where you can't really collect more data. So I think in most cases here, it's sort of best to just go with what you have. And I would be more or less comfortable using statistics that assume normality, looking at this distribution, because it doesn't seem to violate it in any real clear way. But this is one of the difficult parts about applying statistics in the real world, is there's often not one right answer, one way to do things, and sometimes you just have to do the best you can with the data that you have. I'm going to go back to a dot plot here. So again, each data point is a 1 year of World Cup data from one of those three South American countries. The first way we're gonna look at this is I'm gonna look at this by hemisphere, and so we can look at number of goals scored when these three South American countries are playing in the Eastern Hemisphere versus the Western Hemisphere. And there is sort of a little bit of what looks to be maybe an interesting shift here in between these two distributions. And one of the things I would recommend doing at this point is adding some descriptive statistics. And I think if you're trying to ask the question of, are they different from one another, the 95% confidence interval is a good place to start. I'm going to actually add the values to that. And so we can see that, the mean number of goals scored when those three countries are playing in the Eastern Hemisphere is 7.81. And the mean when they're playing in the Western Hemisphere is 10.6. And so that's interesting, because that seems, to be a sizable difference between those. The 95% confidence intervals are still overlapping a little bit. So it's not like a clear statistically significant result. We can actually go ahead and run the t-test here, which is what I'm going to do. And again, if you want to run the non-parametric version of this test, we would run a Mann-Whitney U, and I do that by checking this choose non-parametric tests. But I'm gonna run the t-test here, and you'll get this little pop-up of it communicating to students when you should use this. Well, we're testing for a difference in the average value of a numeric variable between two different groups. And so we've got this grouped, these World Cup performances grouped into Eastern and Western Hemisphere. And we're looking at a difference between average goals. And it works by weighing signal against noise. And the signal is the difference in the means, and the noise is the spread of the data points around those means. So when we actually run this t-test, we get a p-value of 0.09, and we can look at this on this number line here. And this puts us in this range of some confidence that the groups are different, but we're not into the zone of statistical significance below 0.05. And so one thing to think about is if this was a scientific study, the conclusion would be that there is no evidence of a difference in goals scored in between these two hemispheres. But I want you to, we'll kind of think about that and think about that scientific standard of evidence, but also how, we might choose to apply other standards of evidence to this if we're making decisions. But we'll look at this a couple other ways. So another way we could look at this variable of continent. And I'm going to switch out hemisphere on X for continent on X and look at these data this way. And there's a couple of things we can see here. And this is the kind of thing I think you want to encourage students to talk about as they go through a data set visually. But one, you can see that we don't have equal sample sizes here. There's only been 3 World Cups played in Africa in this data set, and relatively smaller numbers of World Cups have been played in Africa, Asia, and North America as compared to Europe and South America. And when we look at where the means are, you sort of see that the means for 4 of these continents are relatively close to one another. But this number of goals scored by South American countries when playing in Europe does look like it's a bit, below what we see for the others. And one way we can maybe zero in on this comparison between Europe and South America is if we go up and we exclude some of these values. So if I go up to World Cup location and I click this values, I'm just going to go and exclude Africa, Asia, and North America, and turn this into a 2-point comparison. And now when we're looking at 95% confidence intervals, we still have a little bit of overlap, but it's getting closer to sort of not overlapping when we do this 2-point comparison. If we go ahead and run a statistical test from here, so I'm going to run the graph-driven test, and we'll run the t-test again. And now we get this result. We see our degrees of freedom 34 there, t-score 1.9, but this p-value 0 0.07. And this could be interpreted as some confidence that the groups are different, but in a a scientific journal article, this would be most likely reported as no evidence for a difference between goals scored when South American countries are playing in Europe versus when they're playing in South America. And this I think is an interesting point to think about what that p-value means, because a student might look at this, especially if they are an avid soccer fan, and they might look at these data points and say, see, I knew it. I knew that there was some truth to this, that this sort of home field advantage kind of effect. And we can think about, we'll say, okay, well, what does the math tell us, and how would we interpret that p-value? And I think rather than thinking of this as a binary, this is a good chance to say, well, that 0.07 value means roughly a 7% chance of getting data with a difference like this and variation like this, if in fact there is no real difference at all. And the point here is there is no infinite population of World Cup performances for us to sample, so we can never know sort of the truth of the universe. We can't just keep sampling until we have very, very high confidence. We're forced to deal with the data that we have. But thinking about what different groups might use as a standard, and a 0.07, now if I was making some kind of sports betting decision based on this would probably be good enough for me. And I think that would be an interesting thing to ask your students. If you're reporting this in a journal, what would you say? But okay, if you were actually laying some kind of bet down on this, how do you feel about this home field advantage? Is it real or is it not real?
I think this also qualifies as being below the significance threshold for a pub fact. Like if I were concerned about where the next World Cup was going to be played, this would be enough evidence for me to think, yeah, I want it to be played in South America versus Europe.
Right. Like it's not this scientific standard of evidence, but there is still evidence. And how you weigh it ultimately depends on what is the seriousness of the decision that you're making, who is the audience you're presenting it to. All of that stuff matters. And this is also a good time to talk about how conservative science is. That the 0.05 threshold for making a scientific claim is pretty conservative, and the evidence has to be fairly strong, certainly beyond the level of a pub fact before you can make that kind of claim. But just because something isn't statistically significant doesn't mean that it there's no evidence whatsoever for it, at least in sort of lay terms. And another thing in thinking about this and sort of indicating that it is not binary, and I think if thinking about it as if you had to place a sports bet on a South American country playing in a World Cup in Europe versus playing in a World Cup in South America, if we move these data points, just a little bit, if we shifted, this data point, this top data point down just a little bit, it would change the p-value, and it might change it to 0.05. But would that really change the amount of confidence you had in that conclusion? Is there really a difference in how you feel about this at a gut level when you have a 0.05 versus a 0.06 or 0.07? And I would say probably not. The like sort of like gut level feeling of, does this pass the eyeball test is probably not going to be changed by the probability value, shifting just a hair to get it over the scientific threshold. So, with that too, a 0.05 is not necessarily the end all be all of results. It's not necessarily ironclad just because you've achieved that standard.
Yeah. And my takeaway too is just it's cool how there's a progression of graphs that we used that arrived at a more significant conclusion. Like we started at when it was 0.09, took a closer look, saw when it was actually 0.07.
Mm-hmm.
But now might be a good time to take a look at how we can take this analysis that we've done and then begin to transition to using this in R.
Yeah, sure. And just to kind of add one more point though, but that, that process that we went through where we're sort of digging through different variables in the data set, you need to, you need to be careful with that, because if you have enough response variables and enough predictor variables with a sort of marginal result like this, you can be sort of deceptive in the way that you present it. And I would argue that like the best sort of science would present all of those results of those different analyses we did, and make a conclusion, but let the reader ultimately determine how much strength they put on it when they can see all of it. Because if you're able to just sort of cherry pick a result, you might not be really telling the whole story if you do it that way. But let's transition to some of the new stuff in DataClassroom U and talk about how we could start exploring how you would make a figure like this in R. And the first thing I'll say is this figure is not made in R in DataClassroom. This is a mix of PHP and the D3 coding library, but this is all working on the back end of DataClassroom, but it is not R that is running back there. I'm going to go over here to the control panel, this graph-driven test button, and I'm going to open this again. And this is where we were right before we launched the t-tests that we did. But you'll see there's also this try it in R button where we can start exploring some of the code. And the thing I want to point out that can be useful to learners is that the code is annotated, and you'll see it's sort of broken up into these blocks, right? Where there's these groups of code, and behind the hashtag is some annotation to what that block of code is doing. And so we can see like this data equals read.csv. This is reading in this CSV file of data. The second section of load the plotter libraries, this is loading the plotter libraries of ggplot and this hmisc. It's putting these or loading these up into R. If we want to see exactly what this code will run, we can click this run it in R button, and it's now spinning up R on a DataClassroom server, and it's executing that code. And you can see it's trying very hard to match the appearance settings as closely as it can. It matched the colors that we were using. It matched showing the mean and 95% confidence intervals with a dot and bars. And then it tried to match fonts as well. It's not 100% perfect. It's not, you'll see there's some small differences, but this is basically how you would make this figure in R. And I'm going to actually kind of show you this exercise that we are in the early stages of building. And what I'm gonna do is open up this as a separate tab. And so what I did was go over to the assignment tab. So these three tabs of table, graph, and then this one that's called getting started. I've got that open now in this tab. And this is the beginnings of an exercise for getting started with R. The first couple of things you will do in this exercise is what we did in building that graph to answer those questions. But you'll see these later questions in the exercise are asking us to use this try it in R function, find the command in R that loads the libraries, find the command that draws the graph and paste it below, points out color can be an important way to communicate with your audience, find the command that sets color for the data points on your graph. So I'll go through, we'll do like this number 4, find the command that draws the graph and paste it below. So what this does is when your students have this code up, this question sort of invites them to look through this code and dissect it. So if we're looking for the code that draws the actual graph, we can see that, well, here is this block of code right here, and it's annotated. It says, this is the run command to draw the actual graph right here. And some of the other parameters have been, specified before it. If we also want to look at, one of the other questions was, what was adding the descriptive stats? Well, this is the section of the code that they would be looking for to see what added the descriptive stats, specifically show the mean as a dot, and doing the stat summary where they're showing those as points. You can see we've got color selected. This is this code, right here. This is specifying that dark blue color that is showing the mean in error bars. And then this 8.0 is indicating, a size there. And then this position nudge has pushed them off to the left. So this is the kind of thing in the early stages of looking at R. We think it makes sense to have students, build these graphs and then start going through some of these exercises where they're dissecting the code like this. And then the next steps would to actually take this code out, drop it in RStudio, and start using it as example code to start working with other data sets. So you could ask them to do a similar task with a totally new data set, and they can start making changes there, start adjusting colors, start adjusting choices like the mean and error bars and all that sort of stuff from that point forward. I want to show you something nifty too for learners. If you've ever taught a class with R, especially if it's been a big class, that loading the data in can be a bigger challenge than you think it's going to be. And so one thing you can do in the early going, this checkbox to include data in the script for data sets of less than 500 rows, it will just drop the data in here. So this is the data table, all the data in it. And so now students can actually just take this whole code and put it in, and you don't have to mess with file paths. You can save that for a second or third lesson if that's the time you want to handle that. Angela, I see you nodding. I'm guessing that you've been through that either as a teacher or a student. Yeah. So you can also, if you do want them to kind of go and start working in R in a less scripted environment, there is this blue button down here at the bottom of the window to download the data as a CSV file. And so, and pressing that button, it will download that data as a CSV. And then, that could be a starting point if you want to have them work through, the loading the data in as a CSV file. And I can uncheck this so we can see, having them use that read.csv command there. Okay. Yeah.
So the next thing on our kind of our learning goals for this presentation was to go through some ways that we can encourage students to make observations that are valid, but don't have to be based on inferential statistics. I think that where we've stopped in the graph view for now is kind of a cool place to go next, because I think a question I would want to know next in kind of the logical progression would be, okay, how do the three countries fare compared to one another? So you can add that to our view.
Yeah. So to do that, like what Blake was talking about, if we wanted to split this out by the three countries that are represented in the data set, I'm going to go up here and add this World Cup location country.
Click on team country. The World Cup location was the specific country of the World Cup.
Of where it was hosted. Sorry, my mistake. I'm going to unclick that. So team country, we add team country there, and I'm going to add them as the Z variable first. And so we get them color coded, Brazil in green, Argentina in the sky blue, and Uruguay in the darker blue. Looking at them this way, could possibly be informative. At least it tells us, we can kind of get an idea of where these countries fall and sort of how they're distributed by country. But I think it's even more informative if students can split these out with this group by Z. So I'm on the right-hand control panel and I check this group by Z. And now we can look at this, look at this pattern comparing when they're playing in Europe versus when they're playing in South America, and look at it by country with the 95% confidence interval. Right away, we can see things like the 95% confidence intervals get pretty large when you have small sample sizes, but we can also sort of see a pattern between the countries that persists in both of the locations, whether they were playing in Europe or South America. It looks, Brazil scored the most goals on average in both of those continents, and Argentina the second most, and Uruguay the third most. So you might make some observations of and try to explain this. You could talk about what might explain this pattern, and it doesn't necessarily need to be statistically significant. This will not be statistically significant. There's not enough data relative to the variation here, but it's still a pattern that students can pick up on, and I would argue it's still a valid pattern for discussion, even if it doesn't meet that threshold for statistical significance.
I see plenty of fodder for casual fans to debate here about Argentina maybe having a more conservative style of play, and that's why they've scored a tighter range of goals in Europe. Brazil has scored a greater variety of goals, so they've got more of a freewheeling, maybe a risky type of style of play. So I love breaking apart like this.
And exactly what you're doing, I think that's a great way to get students familiar with this process of analyzing a data set, is to pick topics that students will be interested in, and also that they may know something about, so that when they see data like this, and you can say, if this is, I don't know, if this is some sort of esoteric phenomenon in biology, and you ask, why do you think the data look like this? What might explain the pattern? Sometimes it can be sort of like pulling teeth to get something put forward that might be a plausible explanation. But when you have people who are working with a topic that they're familiar with, even if they're not data experts, they will sort of naturally start breaking this down and thinking about, why might I be seeing the pattern that I see? And that gives ideas for future research questions. That's exactly the process scientists go through with preliminary data that helps them, write grant proposals and design bigger studies to put ideas that might have merit to more rigorous test.
Having made it through all the topics we intended to cover, might be worth, we could pause the recording and just turn it over to our audience for any Q&A for specific data classroom questions.
Yeah, sure. So before I shut the recording off, I'll just say, thanks for joining us. And then I will stop the recording.